Hey, AP Chemisters, this is Mrs. Vandeloy bringing you Blankwalle Chapter 12, Part 4, Part 2. We've been talking about factors that affect solubility, and we ended up with the last one of Part 1, talking about that temperature will affect the solubility of gases in solution. And we said that the colder the liquid, the more gases are dissolved in water. The hotter the liquid, the less gases are dissolved. It's an inverse relationship. And so that's why we looked at the cold water cup versus the hot water cup. I sure hope you all did that. So if we're talking about gases, it may not surprise you that pressure can also affect solubility, all right? And where have you maybe thought about this before is like if you ever drink some pop, okay? So what happens here, an unopened can of pop is at high pressure. That's how Coca-Cola and Pepsi bottle it, under high pressure. So what happens when you leave an unopened bottle of pop out? The pop becomes flat because all the carbon dioxide comes out of solution. Why? Because now the pressure has dropped and more of the gas comes out of solution. So just listening to this reasoning, if you have a high pressure, you have a lot of solubility. You have more gases that are in solution. As pressure goes down, more and more gas comes out of solution, so solubility goes down. That's a direct relationship, isn't it? The amount of gas dissolved in a solution is what? Directly proportional to the pressures of the gas in the solution, okay? So here we are at equilibrium again, right? So we have so many gas molecules dissolved, you can't see them when they're dissolved, and so many gas molecules out of solution that have already risen to the top. So what happens if I press down on this, all right? So the pressure is increased, all right? So what actually happens if I were to see what's going on, we could count these different gas molecules, all right, and see some of them are recondensing back into the liquid phase. For example, I already count, let's look at these. These are carbon dioxide. So we have 1, 2, 3, 4. We have a whole bunch of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think we have 17 gas molecules right here. If I were to count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think there's only 15 of them now, so 2 of them came into the bottom. And so you have reestablished that equilibrium, where again, the rate of evaporation will equal the rate of condensation. I'm not saying that the numbers are equal, just how fast they're moving are equal. All right, so what's it saying? So more pressure, I have more gases in the liquid phase. The less pressure, the less I have gases dissolved in the liquid phase. So it's directly proportional, all right? So here's our equation. What do you think S stands for? Solubility, and that's our friend molarity, isn't it? I'm just going to skip down here. P. P stands for pressure. Hopefully you knew that. Typically it's an ATM, but it doesn't have to be an ATM. It all depends on your constant. All right, so your constant is your K, and that's molarity per ATM, or it might be molarity per torr, or it might be molarity per millimeters of mercury. So always keep on the lookout for your K value. So it says rewrite the equation to solve for K. Well, if I want K by itself, what am I going to do? Divide by P. All right, and look what happens here. What kind of relationship is this? This is direct. So what do we do? We divide, don't we? And we get our constant. So that works for other things besides, you know, Charles' law and Gay-Lussac's law, doesn't it? So it says Henry's law works best for dilute solutions of gas that do not dissociate or react with a solvent. Got to be careful because carbon dioxide can dissolve and react with water to make a weak carbonic acid solution. So the ones that best work out do not dissociate or react. So because now you've changed the number of gas molecules because you have reacted with them, not just dissolved them. All right, so problem number 9. It says Okay, a certain soft drink, I told you about that, is bottled so that the bottle at 25 degrees contains carbon dioxide gas at a pressure of what? 5 atm. That's the bottlers, that's what they did over the liquid. Assuming that the partial pressure carbon dioxide in the atmosphere is 4.0 times 10 to the negative fourth atm, calculate the equilibrium concentrations in the soda both before and after the bottle is opened. The Henry's law constant for carbon dioxide is 3 point, can you change it to 3.4? I think that was a typo. And then it's moles divided by the quantity liter times atmosphere at 25 degrees Celsius. All right, so what's happening here? We need to do the before and the after. And before I do anything, I'm going to clarify something. Beep, 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 beep. All right, so what pressure am I talking about? The pressure of that dissolved gas. So apparently I have a pressure of 5 atm on that above gas here, okay, in this particular problem, okay? So it's the pressure of that gas, okay? So when I do this, I need to separate this into before and after. So solubility is equal to the constant. Well, I gave you that constant, 3.4 times 10 to the negative 2 molarity. I just changed moles per liter to molarity per atm because it's at 5 atmospheres, okay? So it contains carbon dioxide gas at a pressure of 5 atms over the liquid, okay? So it's of that gas. So when you get out your calculator, oh, if you haven't done so, get it out now. All right, so I'll pause this if you need to. All right, hopefully you got your calculator out. What do you get when you multiply these two things together? Hopefully you got this, all right? 2 sig figs, yes, because of this value, the constant doesn't make any difference. So what about afterwards, all right? So solubility is equal to that constant, but what's the pressure of the carbon dioxide above the liquid? I believe it's 4 times 10 to the negative fourth. All right, I converted that into regular notation. I still kept 2 sig figs though. So when I get my calculator going here, the calculator gives me 3 sig figs, so I just rewrote it as 2 sig figs. Does this make sense? So at high pressure, you have a high concentration of carbon dioxide in your pop. After you leave the bottle open, all right, the partial pressure carbon dioxide is pretty low. Think about how much carbon dioxide is in our atmosphere. Not much, all right? So the partial pressure carbon dioxide is pretty low, and it all comes out, and you have very little left in solution, okay? So problem number 10 is very similar. Why don't you do this? What pressure carbon dioxide is required to keep the carbon dioxide concentration of a bottle of club soda at 0.12 molar at 25? So why don't you go ahead and pause this, do the problem, and come back when you're done. All right, welcome back. Hopefully you did it. It wasn't too hard, I hope. And this is what I got here. So solubility is equal to Kp. 0.12 is equal to 3.4 times 10 to the negative 2 molarity over atmosphere times pressure. So I divided both sides by the K value. I get pressure of 3.5 times, or just 3.5 atm. Why 2 sig figs? Because this is 2 sig figs, okay? Well, these problems all gave carbon dioxide, probably because it's the more common, but if you ever need the other ones, here they are. So this is the end of section 12.4. Don't wait to be great, and I'll look for you in section 12.5. Bye-bye.